This is lecture number 14 for ME 314 Fluid Mechanics 2 course, and the second lecture of this week. In the earlier lecture, we have seen the development of the stream function and its physical meaning, and we have plotted the velocity fields on using a Java applet, and we use Maple to plot the vector fields. And today the lecture content is the first thing today we are going to define here is circulation, and then we will go into the relationship between vorticity vector and circulation, and then we will go through the Stokes theorem, which is actually relating the vorticity vector with the circulation. And then we will solve a problem on circulation by taking a closed rectangular contour. And then we will go into this physical meaning of the divergence of a vector. So if we have a vector field, and if you take the divergence, what actually the magnitude of divergence is representing, this is what we will explore using visualization tools like Maple and the Applets. In the end, we will go into the software part, and that would help our understanding of circulation and line integral and the curl of the velocity vector. Okay, let's start with what is actually the circulation. So actually just think of a closed curve. You have a flow field, and the blue lines are actually representing the streamlines. So at a given point, velocity vector is always v is the velocity vector, and this velocity vector has actually the two components. One component is the tangential component, and other one is the normal component. So for our differential area, as we know that the area is always represented by the normal. So whatever the flux comes out or goes into the region of interest is through in the normal direction. And there is this is what we have already studied in our Reynolds transport theorem, this normal component of the velocity vector. Here, if we look at the nomenclature, Vn, we are calling it a normal component of the velocity. Vt, we is calling it orthogonal to the normal, that would be the tangential component of the velocity. Let's say we on a closed contour, this closed curve, we are just considering a differential length. So the flux part which is coming in and out in this closed contour would be dealing with the normal component of the velocity. What is the role of this tangential component? That is important, because there is no flux coming out in the tangential direction. Whatever the fluid is, that is actually within this contour, this velocity component. Only the fluid coming out from this contour is in the normal direction. Okay, the quantity that is actually the, if you take the differential length and you take the normal component of the velocity, so that would be something what is coming out to this differential element. So that would be, this integral would be integral normal component. If you take that integral over this length, that would be somewhat dealing with actually the what is coming out, and that is something we have represented in the definition of the stream function. So stream function is something where the velocity vector is always actually tangent, but the flux coming out of the region is always through a normal component of the velocity. In circulation, actually, normal component is not the active component. What we now is to think about what will be the line. Actually, this is in the flux, it is an area integral, but here it is a line integral. So you have integrated over S. S is a length, not an area. So keep this in mind. The flux part is actually representing the area in the normal direction. I mean the thing which is coming out. So here we are not calculating the area, flux, but we are actually having an integral, line integral over this differential length, but the velocity vector is in the normal direction. And this is somewhat idea that is important in dealing with stream functions. Whereas this tangential component is actually always remain within the closed contour, and if you see that anti-clockwise direction is the direction of the velocity right here, and what we define is actually the line integral of this tangential component. If you take it over the closed contour, that is actually representing a quantity we have given a name called circulation, and we use capital gamma as a symbol to represent circulation. So circulation is nothing the line integral of the tangential component of the velocity around a closed contour. So you can think of okay, at this differential length there is certain velocity. If you move to this differential length, the tangential velocity would be different. If you move to this differential length, the tangential velocity would be different. If you move to this point, the tangential velocity would be different. So what this integral is actually representing, it is representing the product of the tangential component of the velocity times the length. If you multiply it together, for example, the units for tangential velocity would be meters per second, and you multiply by the meter, you're going to get meter square per second. So it's not the volume flow rate, it is actually meter square per second. So units for circulation is meter square per second. So what physically it represents is nothing, just take the product of the tangential component of the velocity, which is always changing at every point. So if you multiply it with the differential length and take the sum over the whole contour, we are going to get a quantity called circulation, and we use a capital gamma letter to represent that quantity given a name circulation. And this integral is having a closed curve. So this is actually giving us an information that this integral is evaluated over the whole contour, and the whole closed curve is actually the summation is over the whole closed curve, summation of the product of the tangential component of velocity over the differential distance. If you take the sum over the whole contour, this is what it is actually represented. Okay, we can represent this tangential component in terms of the velocity vector v, because if velocity vector v with the tangent makes an angle alpha, so the cos of alpha component would be the horizontal component, a normal component would be the sine of alpha. So sine of alpha would be parallel to the normal vector, whereas the cos of alpha component would be in the tangential direction. So since the velocity is in the tangential direction, that's why we have used v times cos of alpha. So this is a mathematical definition. So I mean, it is important to understand that the word circulation is you should not be confused with rotation actually. So circulation word is actually a terminology, and in fluid mechanics how it is defined mathematically is it is merely a tangent, the line integral of the tangential component and that is integrated over the closed contour. So that is its mathematical representation. So this circulation is just a line integral of the tangential component velocity over the closed contour. Okay, let's see how actually we can think of, for example, for simplicity, we have taken a fluid element which is a rectangular element. So A, B, C, D is representing a fluid element. And let's say that this fluid element is under the transformation of rotation. So it is being rotated, and I have taken anti-clockwise direction is of rotation to be positive. So if you look at this fluid element is having for the length A to B is a differential length dx, and for this differential length the velocity in this tangential direction or in this length of differential direction is u. Similarly, you have B to C is another element whose length is dy, and the velocity here is this is v, and this is v plus how the v changes as you move in the x direction. So similarly for element A to D, the velocity is magnitude is v, and its length A to D is dy. And for an element D to C, its length is dx, and its velocity would be, for example, here the velocity is u. So as you move in the y direction, there is some change in the velocity. U takes place as you move in the y direction. So that would be represented by this term. So what we need to do is we need to take the circulation. Because this fluid element is rotating, and by virtue of this tangential component of the velocity. So tangential means if this contour is ABCD, so in the direction of AB there is a velocity component, in the direction of BC there is a velocity component. So for example, if we have no knowledge about, let's say this element, there is some center, and this element is rotating about the center, and we don't know right now that this fluid element is rotating about which point. It could be this point or it could be the point outside the coordinate system, we don't know. So the idea of circulation is very useful in such cases where you don't know where the fluid element is going to rotate. So what we do is we take a closed contour, and what we do is we multiply the velocities with the differential distances and take the sum in order to calculate the circulation. So this is what we do it mathematically. For example, if we have to calculate circulation of this rectangular element A, B, C, D, so first start with A to B. Its tangential component of the velocity is u, and the distance is dx. So I just multiply u with dx to get one of the part of the circulation. For this whole contour, AB is one part, and then go to the BC part. So this BC part is having velocity component. Velocity magnitude is v plus dava v by dava x times dx, and if you multiply by this length dy, so you get another part of the circulation. So the integral is actually represented this summation, so you are adding them together. And it is important that the velocity is in anti-clockwise direction here for element AB, and for element BC also in an anti-clockwise direction. But for element CD, the velocity is in the clockwise direction. So I have taken not the negative of this velocity in order to calculate this circulation, where we have assumed that it is anti-clockwise. So this component of the velocity, tangential component in the length CD, and multiplied by the length CD. Length CD is dx. Similarly, for element dA, we have velocity minus v, and the length is dy. So this is how actually we have applied the definition of circulation. Circulation is nothing over a closed contour. Just take the product of the velocity times the distances and take the sum. You're going to get the quantity given a name circulation. So for the element A, B, C, D, we have calculated the circulation. Okay, now we can simplify things. For example, as we know, u dx and u dx, it is minus, so it can cancel out. Similarly, v dy and this minus v dy part can be cancelled out. So I have just made a simplification here. So we end up with this part, and what we end up with here is actually the thing that is responsible for circulation is not the magnitude of the velocities, but the gradient of the velocities. And this is quite an important aspect, and we have seen in several of our derivations like continuity equation, momentum equation. For example, in momentum equation, we have learned the net force is due to the gradient of the stresses that is acting onto the surfaces. So the stress that is acting is not creating the net force, but the gradient actually created a net force. Similarly, here you see the velocity change, the gradient of the velocity with respect to x and the gradient of the velocity component u with respect to y is responsible for circulation. So you see dx, dy is common here. What I can do is I can make it a common. So this would be actually an area because dx and dy would be an area of this fluid element. So circulation would be actually this this part in the bracket times the area of the element, or the area of the actually not the element, the whole closed contour. Na? So the closed contour is actually a summation of combination of several elements. Okay. Now we can okay, the term in the bracket is actually the we know, for example, for this two-dimensional case x and y, we have a fluid element in 2 dimensions. So this term is actually representing the the z component of the vorticity vector. Actually, is the vorticity vector, z component of the vorticity vector times the area. So this is what we can write as. So circulation of an element, fluid element A, B, C, D, which is a rectangular element, and we have calculated, which is nothing, the product of the vorticity vector about z, the component of the vorticity vector in the z direction times the area. So that is actually the we can see that the circulation is through this closed contour is actually nothing. You have summed up the vertices because this closed contour is comprising of several fluid particles, and different fluid particles are rotating around their own axis. So that is represented by means of a vorticity vector. So circulation is representing actually the summation of all the vertices that is present within the closed contour. So we can call that to be mathematically like this. So circulation for a closed contour C is representing a closed contour, and I have emphasized this integral as well as this circle over the integral, which is represent this integral is a line integral, and it has to be evaluated over the closed contour. So this v cos alpha is a tangential component of the velocity. If you multiply by the differential distance and take the sum over the whole closed contour, you are going to get the quantity named circulation over the closed contour. And we have learned that for this fluid element, our closed contour is fluid element is comprising of this rectangle ABCD. So for this area, the circulation is simply the product of the vorticity vector in the z direction times the differential area. And this is the differential area of dx and dy. So the differential area of the closed contour. What we can think of physically is actually, mathematically, circulation is a simple idea that just take the line integral of the tangential component of the velocity over the closed contour. Physically, actually, you calculate some number. If you calculate this integral for a given velocity field, you end up with some number, and that number would be giving you the measure of the how powerful the vertices that are being present within the closed contour. So if v as a velocity vector, it has a tangential component of the velocity, and if you multiply all these tangential components which are changing at each and every location, multiply by the areas, you will end up with a quantity called circulation, which is actually the summation of which is actually the measure of the strength of the vertices that is contained within this closed contour. As we can think of, mass is what is a measure of inertia. So more the mass of an object, more will be its inertia. It means it would be difficult to change its position if it has more mass, or we could call it has more inertia. Similarly, we can think of circulation is actually the measure of the strength of the vertices. So if the circulation is a bigger number, it means actually the vertices that is present within the control, within the closed contour, are of bigger strength. As we already know from the earlier class as well, I have already explained that verticity, in the topic of verticity, that verticity is actually the local spin of the fluid particle about its own axis. So we can think of closed contour is comprising of several fluid particles, and there is a rotation of each fluid particle, and that is represented by the verticity vector. So if it is an xy plane, then the thumb, using the right hand rule, we know that the thumb is pointing the direction of the verticity vector. So if it is x direction, y direction, or z direction, whatever it is, so the if curl of the finger is representing the rotation, then thumb will be pointing out, the thumb will be the right hand rule, the thumb will be representing the direction of the verticity vector. Okay, so the idea of verticity is actually of microscopic nature, where actually we are focusing on a particular fluid particle, whereas vorticity is actually the summation of all the vorticities that is present in the closed contour. So the idea of vorticity is microscopic picture, whereas the idea of circulation, which is mathematically the summation of the line integral of the tangential component of the velocity. So when you talk about circulation, you are not interested in each and every individual particle, but you will be interested in the strength of the vertices within the closed contour. So once you calculate vorticity, it means actually you are interested in a particular fluid particle, and more the vorticity of that particle about its own axis, about the axis of rotation. And it is very important to appreciate that the idea of vorticity means the particle is rotating about its own axis, whereas in circulation different particles would be rotating about different their own axes. But once you talk about circulations, you don't know the rotation is something whatever the vorticity is present within the closed contour. So we are not bothered about the rotation of an element in a particular with the particular center of rotation. So vorticity is always about its own axis. The rotation is about its own axis, whereas in circulation we are not bothered. We are interested in the strength of those vertices. So more the circulation, more will be the strength of vertices. So we can call the circulation around a closed contour would be the sum of the vertices within the area of the contour. And mathematically we can write like this, there a theorem called Stokes theorem, which is nothing just the tangential component of the velocity. If you take the line integral, so that is actually representing circulation, or you can write in terms of the vorticity vector times the area. And Stokes theorem is actually just because this vorticity vector is, we already know that this vorticity vector is nothing the curl of the velocity. So, so when you put it in this manner, this is known in mathematics. This is known as Stokes theorem. So nothing. It is a line integral of the tangential component of the velocity, and I mean, we have to write v cos alpha here, otherwise we have to write v tangential. So as you know, it is only the line integral of the tangential component of the velocity. So I missed here writing down cos alpha. So I will write it down cos alpha because otherwise it would be the tangential component. So I mean, you can think of there is a closed region, and the circulation has some direction. Let's say in this particular case it is anti-clockwise direction. So when you calculate this integral, you will be able to calculate circulation, and that is actually there are different particles in this closed contour, and these particles would be rotating about their own axis, forming these vortices. And if you take the take this integral, this vorticity vector times the area, you will be able to get the quantity called circulation. So this, when more the circulation, more will be the strength of vortices that is present within the closed contour. And obviously the area is always represented by the normal, but here the circulation is represented by this closed path, and this closed path here is shown in the red color at the edges, and the arrow is also red. So that is actually representing the circulation, which is the sum of the vortices that are present within this closed contour. Okay, now go to this problem. I mean, let's say we have a velocity field given. So the velocity component in x is u is x squared, v is 2xy, and what you need to do is to calculate circulation around an area bounded by these coordinates. So 1, 1, 2, 1, 2, 2, and 1, 2 are the coordinates. So what I need is I need velocity for AB element, velocity for BC and CD, and multiply by these lengths to get the circulation. So let's see how we do this. Technically speaking, we know that circulation is the line integral of the tangential component of the velocity. So here I have put it correctly. Either I should write v cos alpha or vt. This line integral, because here is not area integral, it is a line integral. And since velocity has it could be have component in general u, v, and w, and these differential lengths would be dx, dy, and dz. So forget about z component because it's a two-dimensional problem. So what you need to do is take the closed contour and calculate this integral. So for example, for the element AB, my velocity is in u direction. Similarly, for element BC, my velocity would be in the v direction. And for CD, the velocity would be in the negative x direction. We will, right now, we have not put any sign here, but later we will do the sign as well. And v is the velocity in this dA direction. So circulation is nothing, the velocity multiplied by the length and take the sum. So as I know the component of the velocity is given to me is x square and v is 2xy, so substitute these components here and look at those limits of the integral. For example, in the first integral, which is from a to b, so your x is changing, from 1 to 2, y remains the same. So your x is changing as you are moving from a to b, and your y remains the same. So y is always 1, y is not changing, y is 1 here, y is 1 here. Only thing that is changing is x changes, y is 1 here, y is 1 here, x changes from 1 to 2. So y is 1, and since x is an integral, so x changes from 1 to 2. So this is how I have to put. and the velocity component is x squared. Similarly, for element BC, we know the velocity is 2xy, and we have the limits of that integral is here x is 2. So at B x is 2, at C x is 2. Only thing that is changing is y from 1 to 2. So my independent variable is y, and y changes from 1 to 2 here. Similarly for CD, here x is changing, y remains the same, so y is 2, and x changes from 2 to 1. So why I have not put minus sign? Because my integral is from 2 to 1. So if I am moving from 1 to 2, I am increasing. From 2 to 1, I am decreasing. So that this limits would bring the negative automatically here. So I should not bother putting a sign here. Similarly, for 1 to B to C, y is positive, but from D to A, y is negative. So because I am moving from 2, y is 2 here and y is 1 here. X remains the same. So x is 1, y changes from 2 to 1. Okay, and then the very simple thing is to evaluate these integrals. X square is x cube upon 3, and here the independent variable is y, so x is a constant. So just I have substituted the value of x is 2 here and integrated with respect to y. So here integrated with respect to x and y. So just I have evaluated some numbers and we end up with the magnitude of the circulation for this closed contour. It means there are vorticities that are present within this closed contour, because circulation is not zero, it comes out to be positive number here. So that is representing, if number is 6, it means the strength of the vertices is stronger. If number is 12, it is much more stronger. If the number is smaller, it represents the strength of the vertices within the closed contour is of less strength. Okay, now we go to the concept of divergence of a vector. So we already know, let's say you have such a field, initially you have a small size vector, and as you are moving horizontally, your magnitude of the vector is increasing. So if you just look in this region, what is coming in and what is going out. So divergence actually represents what is going out minus what is coming in. So if a bigger vector is going out, lesser is going in, so the divergence would be positive. So that is the idea. When you have a positive divergence, it means at the area more fluid is coming out compared with less is going in. So that's why you have a positive divergence. Similarly, if you plot it a negative divergence, it means your velocity vector is bigger and then it is going smaller. So the negative means it is actually the magnitude is decreasing. So it means more is coming in, less is going out. So divergence is always out minus in. So out is less, smaller number, in is a bigger number. So that would result into a negative divergence. If there is no change takes place, whatever is coming in, the same is leaving. So that would be called as zero divergence. So we can plot all such things on a software as well. I mean, I will now switch to the Applet. Let's look at this Applet. I mean, there is a provision of having a user-defined field. If I go into the bottom, I can see a setup, a user-defined field. I just click on that. So now I can have my own field. For example, for the previous case, as we have already done for 0.3x is the u component and z component, just if I take it like this. So here x is nothing, 0.3 times of x and y is 0. So if I just plot it this way, and I can see, okay, I don't see here the velocity vector. Okay, just go to this velocity vector. Okay, since the strength is not that much, so you can see initially they are smaller in strength, but at the outside they are bigger in strength. And this thing, something can be shown on this maple as well, because if you go to tutors, vector calculus, vector fields, so you have vector field applet for 2D. I just plot z to be my x to be my 0.3 times of x, comma y is 0. And for a stream function, because I'm moving from left to right, so what I do is at y2 and x1, I just put some vectors. So okay, so initially you are less, and then as you are moving you are much bigger. So this is maybe for x, I put a constraint for x 0 to let's say 10, and this one 0 to 5. Okay, so I see here initially the velocity vector is smaller in size, and as you are progressing in x it is getting bigger. So if I ask to animate, and you see initially speed is slow, and thus as it is moving in the x direction it speeds up because the magnitude is increasing. So what I do is initially its speed is low and then it is increasing. So actually at the outside, at the exit there is more velocity, and what is going in is less. So if area remains the same, it means there must be a positive divergence, and that is what is seen here in this applet as well. Okay, how can we evaluate? So actually you see initially it is smaller in strength. Actually it is the color is representing the magnitude. Field magnitude is representing by the color. Okay, how can I see it is a positive strength? So what I do is I go to the surface integral, and I just put a surface integral. So I see that there is a net flux. So more out, less in. So my flux is a positive number here. You see the flux is positive here. Or another way of looking at a positive flux is we can think of this color instead of field vectors. I go to the color of the divergence. So my color of divergence is green. Green here is positive. So for example, my color is none, then it would be gray in color. So gray represent there is no strength actually. So once I put it a color of the divergence, then it means everywhere I have the green, it means a positive flux. So if I evaluate flux here, it comes out to be positive. If I evaluate in this quadrant, it is positive. If I evaluate in this, it is positive. The more is going out, less is coming in. So that is actually the representation of this positive flux. And if we go to this example of negative flux, it means my example velocity vector would be 1 by x. So let's say if I go to this on this just put it 1 by x as my one component of the velocity, because as x is increasing the magnitude is decreasing. So now you see initially x is bigger, and as we are proceeding it is decreasing. So it means that it is more in, less out. So less out means out minus in would be a negative number. So that should be representing negative of the divergence. So if I animate, I see that initially it's a very high speed and then it slows down, slows down. So that is the representation of this streamline. Higher speed and then slows down, slows down. So, and the same thing we can see on this Java applet. If I just put it here, a vector field like 1 over x. Okay, I immediately got a negative sign because my color is divergence. Let's say if I have no color, or just put a field magnitude as my color. So I can see that initially the strength is higher, but as I move here, the divergence is, and the surface integral I evaluate comes out to be negative flux. So it means negative flux means less out more in. So that would be a negative case. Na? So if my case, another case is, let's say my I have some constant field, neither bigger nor smaller. Let's say 2 is my field, let's say. So everywhere have a same vector. So in that case, if I see the plot here for constant vector, let's say a constant vector, so everywhere it is same. So it means the flux is 0 here, neither positive nor negative. So if I go to the color of the divergence, I would be getting gray. Gray means neither green is positive, red is negative. So gray is neither positive nor negative. So everywhere my gradient is 0. So this is how you can see the gradients. Okay, if you see the line integral, the curl is actually representing like this. So for this particular field, the curl is 0. So here you have no curl. Na? For example, if I change my field from x component is I take it minus y, and y component I take it as an x. So if I do it, so I see, for example, right now I see the field magnitude. So my what I see here is the vector fields are curling around in an anti-clockwise direction, and I see a positive color. So if I calculate a line integral, I will get a circulation, positive circulation. So wherever I go and I see a positive circulation. You know. For example, if I change the sign of this field, let's say reverse this, and if I now see, so I get a negative. Negative means my circulation is negative. Na? And if I plot my curl color, so I got a negative color because it is clockwise, and clockwise circulation is negative. And if I just reverse the sign, I would get a positive circulation. And if you want to see how the particles are moving in this field, you can go to the particle velocity, and you can see, okay, there are a lot of particles, the field strength is low, so I increase particles. So particles are moving in a circle. So that is actually, and if you want to see the detecting the curl, you can do this curl as well. For example, if you go to the curl detectors, display curl detectors, and so instead of you see this divergence, the circulation is non-zero. So it means this I remove some of the strength and some of the less particles. So you see particles are in rotation, and at the same time particles are rotating about their own axis. So it means their circulation is non-zero. So there is a vorticity vector present, and circulation is a product of vorticity vector times the area in the closed contour. So if circulation is non-zero, it means the curl of the velocity is non-zero, and this is representing the curl that the velocity is being rotating. So in the previous lectures I gave you different fields where you have a rotational field and irrotational fields. So for rotational fields you will always find a non-zero circulation, and for irrotational field where divergence of the velocity is zero, the curl of the velocity is zero for irrotational field, then you will find that the circulation would be zero, and these curl detectors would be somewhat just rotating or moving, but they will not be moving about their own axis because their vorticity is zero. So this is how you can visualize divergence. Line integral is representing the circulation part, surface integral is representing the flux part. So flux is zero here because it is in divergence of the velocity is zero. And if you see the line integral is some positive number because there is an anti-clockwise rotation. But if I change the sign, then I see a negative circulation, and the curl of the color is also red, which is representing a negative circulation. Yeah. So this is how you can visualize divergence curl, and at this point I end the lecture, today's lecture.